And so to question 9. Speedway airline flies from city A to city B. The flight time is normally distributed with a mean of 260 minutes and a standard deviation of 15 minutes. Before I do anything else, I'm going to write that down. X is distributed normally, mean 260, standard deviation 15, so variance is 15 squared. A flight is considered late if it takes longer than 275 minutes. Calculate the probability of flight is not late. So part A, that would be the probability that X is less than or equal to 275. And I can just use my GDC for that. I go into Menu, Stat, Distributions. I have a normal distribution. And because I want an inequality, I use the cumulative distribution. So NCD. I make sure my data is a variable. My lower value, because I want less than or equal to 275, is effectively minus infinity. I can't quite do that, but I can get pretty close with minus 10 to the power of 99. My upper value is 275. My standard deviation is 15 and my mean is 260. And that gives me that my probability is 0.841 to 3SF. Part B. The flight is considered to be on time if it takes between M and 275 minutes. The probability that a flight is on time is 0.830. Find the value of M. So if I think about this, I have the probability that M is less than or equal to X is less than or equal to 275 is equal to 0.830. If I think about this on a graph, therefore, I have my distribution, I have 275, I have M, I know that this area here is 0.830. I also know that this area here, above 275, is 1 subtract 0.841. Because my probabilities must add up to 1. And so I can check that. So 1 subtract 0.841 gives me 0.159. And therefore my probability X is less than or equal to M. This value here is just 1 minus 0.830 minus 0.159, which is 1 minus 0.830 minus 0.159, 0.011. In order to then work out M, I have a probability, but I need to work out my value. So I go into Stat again, and I need my inverse normal distribution. My tail is to the left, less than or equal to. You can see that on the diagram. My area is 0.011. My standard deviation and my mean remain the same. And so M is equal to 226 to 3SF. Then we get more complex again. During a week, Speedway has 12 flights from city A to city B. The time taken for any flight is independent of the time taken by any other flight. That sentence should be screaming out binomial distribution to you. You've got a fixed number of trials, you've got independent trials, and you've got success or failure, but on time or not on time. So I'm going to write out my new variable. Y is distributed binomially with n, number of trials 12, and probability of being on time, success 0.830. I must calculate the probability at least 7 of these flights are on time. So Ci, this probability X is greater than or equal to 7, which is 1 minus the probability X is less than or equal to 6. You could have half a flight being on time. So I can work this out then. Once again, GDC, I go into Menu, Stat, I was already there. It's a distribution. This time it's a binomial distribution, and I want an inequality, so my cumulative distribution. It is a variable. X is equal to 6, that's what I'm less than or equal to. Number of trials is 12, probability of success is 0.830. And that gives me 1 minus 8.7517 times 10 to the minus 3, which, going back to my normal calculator, is 1 minus 8.7517 times 10 to the minus 3, which is 0.991. C part 2 is more complex. Given that at least 7 of these flights are on time, find the probability that exactly 10 flights are on time. So that's the probability X is 10, given that X is greater than or equal to 7. And the relevant equation here is the probability of A given B is equal to the probability of A intersection B, that is both things happening, divided by the probability of B, the given thing, happening. So here that's the probability that x is 10 and x is greater than or equal to 7. That's a reductive statement. If you're greater than or equal to 7, you must... if you're equal to 10, you must be greater than or equal to 7, divided by the probability that x is greater than or equal to 7, which is just the probability that x is 10, because if x is 10, it must be greater than or equal to 7, over the probability x is greater than or equal to 7. Once again, using my GDC, I go menu, stat, I've got a distribution, it's binomial. This time I want the probability x equals something, so that's BPD. X is equal to 10, everything else stays the same. I get 0.2959297 divided by x greater than or equal to 7. We already had 0.991. So I want 0.296 divided by 0.991, which is 0.299 to 3 SF. So how can we make this more complex? Part D. Speedway increases the number of flights from city A to city B to 20 flights each week and improves their efficiency so that more flights are on time. The probability that at least 19 flights are on time is 0.788. So I have a new distribution. Z is distributed. It's still binomial, fixed number of trials, independent events, success or failure, on time or not. Number of trials is 20, but this time I don't know P. What I know instead is that the probability that Z is greater than or equal to 19 is equal to 0.788. Or alternatively, the probability that Z is equal to 19 plus the probability that Z is equal to 20, that is greater than or equal to 19, is equal to 0.788. And using my formula book, I have my formula for the probability that Z is equal to some specific value. So I have n choose r, so 20 choose 19, p to the power of r, p to the 19, q, that's 1 minus p to the power of n minus r, 20 minus 19 is 1, and then plus n choose r, 20 choose 20 is 1, p to the power of 20, q to the power of 0 is equal to 0.788. I can simplify that a little further. 20 choose 19 is just 20, so I've got 20 p to the 19, 1 minus p, plus p to the 20 is equal to 0.788. And that looks too complex to solve analytically, so let's just do it on our GDC. I'm going to do it graphically, so I go into my graph app, and I plot two graphs. I plot 20 x to the 19 times 1 minus x plus x to the 20 as one graph, and I plot 0.788 as my other graph. Where those two graphs intersect is where left-hand side equals right-hand side is where my solution will be. Now that is a horrible, ugly graph, but it does do what I need it to do, because I just need to find the point of intersection. It looks something like that. So I'm intersecting. I care about my first intersection only. So I G-solve, intersect, and I get 0.957, 0.788. Just to check my next point of intersection, that would give me a probability greater than 1, so that's not useful to me. So that gives me my solution. P is equal to 0.957. Looking at my mark scheme for this question, for part A, you get both marks for writing down your final answer, because you're just using a GDC, but do show some working, it'd be sensible. For part B, similar again, but once again show some working, advance an argument, graphical arguments are great. For part C, you get 1 mark just for recognising binomial, writing the word binomial. Then you could sum probabilities, but your GDC does this for you, so as long as you wrote binomial down somewhere, you could get all marks for this. And then part 2 of part C, you get 1 mark for probability x is 10, then you're using your given formula, getting your correct final answer. And then part D, you're setting up your equation, trying to solve it using a graph, getting your final answer. And you must show that working. That is, you must write down what you're doing, and then you must sketch the graph that you're solving. And another 15 marks, sorted.